So welcome to this next video in the playlist on Galois theory. In this video I'm going to talk about radical extensions, which is a really important concept in the proof of the non-existence of a quintic formula in any characteristic zero field, and indeed then the proof that there doesn't exist a formula for any higher degree polynomials beyond degree 5 in any characteristic zero field. So I'll just put that title, Radical Extensions. And this concept is relevant to any characteristic zero field. So although the proof that we're heading towards we're only going to do for characteristic zero fields, we will define this concept of a radical extension in full generality for any old field. So let f then be some field, and let k be an extension of f. We firstly need to define the concept of a simple radical extension, and then from that we'll define what it means for an extension of f to be a radical extension. So simple radical extension first. So a simple radical extension is a simple extension, meaning that it's achieved by joining on a single element. So if k is a simple extension of f, it means that k is equal to f adjoin some alpha, where alpha is some element of k. So there's a primitive element, basically. So you can achieve the entire extension by just adjoining on a single element. So that's what it means to be a simple extension. To be a simple radical extension, it means that that element, the generator, the primitive element, has to be a radical of some element in the base field f. And what does that mean? It means that if you raise it to some power n, where n is a natural number, where we're taking the natural numbers to be starting from 1, you know, there is a controversy as to whether it starts from 0 or whether it starts from 1, but in all of my videos, I'm going to have the natural numbers starting from 1, which I think is more common. So alpha to the power of n is going to need to be some element of f. That is what it means to say that alpha is a radical of some element in f. It means that it's the nth root of some element in f, meaning that if you raise it to the power of n, it's going to give you some element in f. So if an extension is a simple extension generated by an element that is a radical of the ground field, then we call it a simple radical extension. So let me give you an example. So we will go to our favorite field, which is the rational numbers, and let's say we join on the, let's say, fifth root of 2, and I could have put anything there, but 5 will suffice. So this extension here, q to q adjoin the fifth root of 2, this is a simple extension because it's achieved by joining on a single element, the fifth root of 2. And it's also a simple radical extension because that element, the fifth root of 2, if I raise it to the power of 5, I get 2, and 2 is certainly in the ground field, the rational numbers. So therefore it is obeying this condition here. So that's a simple radical extension then. Or it's an example of a simple radical extension. And I would just like to say one little thing, which is that I'm calling this element the fifth root of 2. Now, obviously, the canonical fifth root of 2, the canonical thing to mean when I write this, is the real one, the one that's in the field of real numbers, that one. But of course there are 5 fifth roots of 2 in the complex numbers. There's the fifth root of 2, the real one, and then there's the fifth root of 2 multiplied by zeta 5. So I'll just write this here. So the fifth root of 2 multiplied by zeta 5, where zeta 5 is the canonical primitive fifth root of unity in the complex numbers, i.e. it's e to the 2 pi I divided by 5. So this is in the great big field of complex numbers, which we know is algebraically closed, the fundamental theorem of algebra. So you could actually put an I here, where I can be 0, which would give you just the real one, 1, 2, 3, or 4, and all of those are going to be fifth roots of 2 in the complex numbers. So when I have put here the fifth root of 2, it could have actually been any of them, because they're all things that raised to the power of 5 gives 2. And what does this symbol here mean? It really just means any element, or it means some element which to the power of 5 is equal to 2. So just like in the more simple case where when we took like the square root of 2, there were two actual things which square to give 2. There's the square root of 2 and then there's the minus that square root of 2. And we agreed that by the square root of 2 we would mean the positive one. Similarly here I'm obviously taking the convention that we mean the real one, the positive real one. In more general cases, you know, if it was the 6th root of 2 then the minus 1 would also be there, so it wouldn't be enough to just say the real one. In this case it is enough to just say the real one because the other 4 aren't real. But more generally we mean the positive real one when we put that radical symbol there. But of course, you know, one of the central themes of Galois theory is how actually all of these are kind of algebraically equivalent. If you join on one of the other ones, the field that you get is absolutely isomorphic, so all that's different is the symbol. So equivalently, I could have replaced my canonical 5th root of 2 with any of these in here, and it would still be a simple radical extension. Anyway, so now let's go over apologies for the motorcycle exploding outside. Well, not exploding, but you know, it's exhaust making a racket outside. I've got my window open because I like the fresh air. So a radical extension then. So this is what a simple radical extension is. So I might actually continue with the example to show you what a radical extension is. So I'm going to now make an extension of this field, and I've run out of space, so I'll do it up here. So if we take the rationals, adjoin the 5th root of 2, and we then adjoin something else onto this, so another radical, but now something that's in this field Q adjoin the 5th root of 2. So if I adjoin on, let's say, the square root of 6 plus, let's say, 2, the 5th root, oh, this is becoming a mess, but hopefully you can see what I mean. So take 6 plus 2 times the 5th root of 2, and I just made this up, and then take the square root of that, and then adjoin that on. So the extension going from Q adjoin the 5th root of 2 up to Q adjoin the 5th root of 2 adjoin the square root of 6 plus 2 the 5th root of 2. This again is a simple radical extension. So this one is a simple radical extension and this one is a simple radical extension. And this is a simple radical extension because this thing we've adjoined on here, this is a radical of something in this field here. 6 plus 2 the square, 2 the 5th root of 2 is in this field here. And we've then taken the square root of it, so we've taken a radical of it, so this thing to the power of 2 is in here. So therefore this is satisfying the definition to be a simple radical extension. It's achieved by joining on one element that is a radical of the base field. However, if you now consider the composite extension, so if you consider this entire thing as an extension of the rationals, then it's no longer... Well, it's probably no longer the case that this is still a simple radical extension. If it somehow manages to still be a simple radical extension, it's certainly not obvious to me what the alpha is in this case. What is the single element that you can adjoin on, which is a radical of something in the rational numbers? You might... Sorry, just having to re-record this final bit because I accidentally said my real name. So you might say to me, this thing here, this looks like a... surely I could achieve this extension by just adjoining on this element, which looks like a radical to me. That's true, you know, this is a simple extension. If you adjoin onto the rationals this element here, that will give you this field because, you know, once you've got this element in, you've got to have it square in, so you'd have to have 6 plus 2, the 5th root of 2 in there, then you'd have to have that subtract 6 in there, then you'd have to have that multiplied by 2, which would give you then the 5th root of 2 is forced to be in there as well. So this would be this entire thing. So it is a simple extension. However, this element, the square root of 6 plus 2, the 5th root of 2, that is not a radical. At least it's not obvious at all that it's a radical of something in the ground field. So I mean, it might end up being the case, you know, if you raise it to the power of 6, I doubt it's, no, raise it to the power of 10, I doubt it will work. In fact, I'm pretty confident it won't work, because it's not going to be a root of the x to the power of 10 is equal to some rational. It's going to instead be the root of some more complicated degree 10 polynomial. You know, you're going to have to take x squared, subtract 6, multiplied by a half, all of that to the power of 5 is equal to 2. That's the polynomial it's going to satisfy, not which is not going to be a nice simple polynomial of the form x to the n is equal to some rational. So even though it's a simple extension with that element, it's not a simple radical extension with that element. And if it is a simple radical extension for some other element, it's certainly not obvious what that element is. And it's more likely, I think, that it's not a simple radical extension, that there is no alpha which satisfies this definition. However, this composite extension here, the rationals up to this thing up here, this is still a radical extension, and that's the definition of a radical extension. It's an extension that is built out of a finite number of simple radical extensions, one on top of the other. So this is built out of two simple radical extensions on top of one another, and therefore is a radical extension. So we can take this further, we can generalize this. So in general then, a field K over F is called a radical extension if it is the case that K is achieved by joining on a bunch of elements, which we'll call alpha 1, alpha 2, all the way up to alpha n. Note, n is finite. And it is the case that for each one, if you take it, so if I take alpha I, where I is 1 to n, and I raise it to the power of some mi, it will be an element of the field that preceded it. So it will be an element of f adjoint alpha 1, alpha 2, all the way up to alpha I minus 1. So this means that for alpha 1, it would have to be an element of, it's to some natural number power would have to be an element of f. For alpha 2, it to some natural number power, and the natural number, note, I've indexed it I because it could depend, it's not going to be, doesn't have to be the same for all the alpha I, it will depend on I. So alpha 2 will have to be an element of f adjoin alpha 1, then alpha 3 will have to be an element of f adjoin alpha 1 and alpha 2, and all the way up to alpha I will have to be an element of f adjoin alpha 1, alpha 2, all the way up to alpha I minus 1. That's the definition of a radical extension. Now, before we end this video, I'm not going to tell you, by the way, why. I'm not going to link this to the existence of formulas yet. We'll do that in the next video, which will be entitled Solvability by Radicals. Here, I want to prove one little theorem that is not difficult to prove at all, and which will be very useful to us later on when we try and prove the non-existence of a quintic formula. And that is that if you have a field, a ground field F, and you have two radical extensions of it, which I'll call R1 and R2, R just for radical. These are not rings, well, they are rings, because of course all fields are rings, but they're fields. The R is for radical. And if you take the compositum of the two radical extensions, you take R1, R2, and hopefully you're aware of what the compositum of two extensions means. It means the smallest field extension that contains both of them. And of course, we know this exists because we believe in Steinitz's theorem. Provided you believe in the axiom of choice, then you believe in Steinitz's theorem, which tells us that algebraic closures exist of fields. So F bar will exist, the algebraic closure of the field F. And these radical extensions, because they're built out of a finite number of simple radical extensions, they are going to be finite extensions, and therefore they're going to be algebraic extensions, and therefore they're going to sit inside the algebraic closure, and therefore you can look at the smallest subfield of F bar that contains both R1 and R2, and that's what we mean when we say the compositum of R1 and R2. So the claim is that if R1 and R2 are radical extensions, then R1, R2, the compositum of R1 and R2 is also a radical extension. So how do we prove this? It's easy. So we say R1 is going to be F adjoin some alpha 1, alpha 2, all the way up to alpha, let's call it M1. So this is just the definition of R1 being a radical extension, and it's the case that alpha I to the power of ni is an element of F adjoin alpha 1, alpha 2, all the way up to alpha I minus 1. So I've just repeated what I've said above about the definition of a radical extension. Similarly, R2 is a radical extension, so I can also write this down for R2. So it will be F adjoin, let's say, beta 1, beta 2, all the way up to beta M2. and it will be the case that beta I, or maybe I'll just use j, beta j, and then I need some other letter, will have h, to the power of hj is an element of f adjoin beta 1, beta 2, all the way up to beta j minus 1. Good. So that's just the definition of R1 and R2 being radical extensions of f. Now, what then will be the compositum of R1, R2? So, because it's the smallest subfield that contains both R1 and R2, it will have to contain all of their generators. So all of these elements, the alpha 1, alpha 2, all the way up to alpha m1, it'll have to be in R1, R2. And all of these elements, beta 1, beta 2, all the way up to beta m2, they'll all have to be in R1, R2 as well. So therefore, R1, R2 is going to be f adjoin alpha 1, alpha 2, alpha 3, all the way up to alpha m1, and then beta 1, beta 2, all the way up to beta m2. Because you've got to contain all of those elements, and if you look at this extension, which contains all of these, it certainly contains both R1 and R2, and it's the smallest possible one that can contain R1, R2, because by definition this means the smallest field extension of f that contains all of these elements, and it's got to contain all of these elements to be the compositum of R1, R2, ergo this is the compositum of R1, R2. So why is this still a radical extension? Well, for the alphas, it's going to be the case that all of these, going up each time, it is going to be a simple radical extension still, because it was a simple radical extension here. Alpha 2 was in f, alpha 2 here was in f adjoin alpha 1, alpha 3 was then in f adjoin alpha 1, alpha 3 to some natural number power was in f adjoin alpha 1, alpha 2, alpha 4 was then in, alpha 4 to some natural number power was in f adjoin alpha 1, alpha 2, alpha 3. So that's still going to hold here, because it's exactly the same fields that precede them here. It's just now for the betas that we have to be careful. And by the way, some of the alphas and the betas might coincide. That doesn't damage the argument at all. So i.e. some of these, alpha 1 might be the square root of 2 and beta 1 might also be the square root of 2. That doesn't damage this argument at all. It still holds. Now we need to argue, why is beta 1 to some natural number power going to be in f adjoin alpha 1, alpha 2, all the way up to alpha m? Well, it's obvious, because beta 1 to some natural number power was in f. So it's certainly going to be in this much larger field, which is f adjoin alpha 1, alpha 2, all the way up to alpha m. Similarly, beta 2 to some natural number power was in f adjoin beta 1. So it's certainly then going to be in this much larger field, which is f adjoin alpha 1, alpha 2, alpha 3, all the way up to beta 1, and etc. So we can write this out. We can say beta j to the power of hj being inside f adjoin beta 1, beta 2, all the way up to beta j minus 1, well, this is contained inside this larger field, which is f adjoin alpha 1, alpha 2, all the way up to, and then we'll have beta 1, all the way up to beta j minus 1. So, because this is a much larger, because this is a much larger field, the condition certainly still holds. So because this is in this, it's certainly true that this is in this. So the radical condition still holds. Each of these, adjoining on each one of these elements is still going to be a simple radical extension. So this overall field is still produced by doing a successive bunch of simple radical extensions, a finite successive bunch of simple radical extensions. So there is the proof that the compositum of two radical extensions is a radical extension. Now, by induction then, if you take the compositum of a finite number of radical extensions, say we have R1, R2, all the way up to Rn, if you take the compositum of them, R1, R2, Rn, that will still be a radical extension. So you might wonder, why do we care? But one day, in future videos, we will care about this fact. So store it in your head. So we'll end this video here, and in the next video we'll do something far more exciting, which is we'll talk about why this is so relevant to formulas.